So last time we were looking at the Schrodinger equation for a two-body system, right? So I'm just going to give a brief overview of that. So the Hamiltonian of the two-body system has two terms, two kinetic terms for the first particle and the second particle. So this is P1, P2. These are the momenta of the first and the second particle. In our case, these particles are the electron and the proton, or one is proton and two is electron. So this is the free part, but of course there is some interaction between them, which makes it interesting. And the interaction we wrote down in the CGS unit to be the difference, the distance, the relative position vector. And if we were to use MKS unit, it's not very hard. We just have to have 4 pi epsilon naught here. Okay, so I'm not going to use MKS unit. So, but later when I write down the energy eigenvalue formula, I'm going to show what the expression looks like if we had used MKS unit. So the Schrodinger equation is simply going to be the Hamiltonian operator H acting on some wave function, and this wave function is now a function of x1 and x2. And we are solving the time-independent Schrodinger equation, so there is no time dependence. So E of t is the eigenvalue, the total energy eigenvalue. So this is the equation we want to solve. And it's a two-body problem, but because of the symmetry of the equation, we see that the Hamiltonian really only depends on the relative position of the two particles explicitly, right? So therefore, we know that there's going to be a separation of variable, so which becomes clear if I introduce a coordinate for the center of mass, and this is a 3-vector whose components are big X, big Y, big Z, and that's given by M1 R1 plus M2 R2 divided by M1 plus M2. This is the definition of the center of mass. And then we can define the relative vector, so the position of the electron relative to the proton, and it's going to have components small x, small y, and small z, and that's going to be just R1 minus R2. So then what we did is that we expressed the Schrodinger equation in terms of these variables. And if I do that, then I'm going to skip some steps. We get h squared by 2m. We get two kinetic terms. And here, let me call this a big M to big M. And then this is going to be the Laplacian operator with respect to this coordinate. So that's why I'm writing it as R, acting on the wave function. And then there will be another kinetic term, h squared by 2 small m, and then another Laplacian operator acting on psi minus e squared by r squared psi equal to et of psi. Here, the Laplacian operator is made out of like the nabla operator, where this thing is d by dx, d by dy, d by dz. So all these coordinates are the big coordinates, capital coordinates, and the the delta operator over here, that's just going to be d by d small x, d by d small y, d by d small z. Okay? Any questions so far? Oh, the other thing is that we define big M to be M1 plus M2, and small m is M1 times M2 divided by M1 plus M2. Okay? And this is also known as the reduced mass.